Yes, so as Hartmut has already said, I have the honor of starting this school and doing so with the topic of spectroscopy and scattering formalism. So I'm sort of on a team with Jeremy Green, who's sitting in the back, who will present applications. We've coordinated to some extent, and we also convinced ourselves that hearing some overlapping ideas in a different perspective is not a bad thing. So I think it will be complementary and hopefully enjoyable. My plan is to use a mix of slides and the chalkboards here for the presentation style. I hope that works as well. And because I'm the first speaker, I would like to give sort of a broad brush overview of how we might think of lattice QCD before we zoom in on the more technical topic of formalism for spectroscopy and scattering. So let's start just a few minutes with a bigger picture. So I think all of us are working in lattice field theory, are familiar with it, but it's still entertaining to think about how do we describe it and how do we describe it to different audiences. And so to sort of a general audience of physicists, one thing that we might say is that lattice field theory gives us a non-perturbative way to regulate quantum field theory. So we know that QFTs are plagued with ultraviolet divergences, and we need to come up with a definition that makes things finite, and we call that a regulator. And if we don't want to rely on a perturbative expansion, we need a non-perturbative regulator. And in this case, we also achieve a systematically improvable numerical method, which means however well we can calculate something today, there is a roadmap down the future where we can systematically get better and better with a reliable result and a reliable uncertainty. And in an even bigger picture story, I would argue that it's really an exciting, vibrant, and highly active research community, as evidenced by all of you here. And it's also a very technical field, which means I think many of us are always thinking, how do we communicate this effectively? And I like to show this work from the University of Adelaide, where they're visualizing gauge fields to try to sort of think about this in a way that might be accessible also to some non-laticists. Now, zooming in on QCD, I would say what we're really talking about here is a recipe for strong force predictions. So we start in the context of the standard model of particle physics, and then we say, well, what do we have? We have the electroweak force, and we have the strong force, the quantum description of which is quantum chromodynamics, or QCD. And how do we implement that in practice? Well, first we have a Lagrangian. So this Lagrangian density is this elegant, simple formula that tells us how quarks and gluons interact and what are their basic properties. That's the Lagrangian defining the theory. Then we have lattice QCD as a formal / numerical machinery, because if I just have this by itself, I don't know how to use it to calculate any experimental predictions. I need this formal / numerical machinery as sort of the second part of my recipe. And crucially, I need a few experimental inputs. And it's amazing how many times non-lattice people have come to me with some confusion based on the fact of how does your computer know about nature at this level of detail? And the answer is always we sacrifice a few things. We don't predict, say, the pion mass, the kaon mass, and the omega baryon mass, but we take those as inputs. And after sacrificing a few inputs to tune the numerical simulation, then everything else is an output, either a pre or a post diction. And here's a circle of the kinds of things you might imagine predicting using numerical lattice QCD. And I would emphasize that what is in this circle are things that lattice QCD does very well at very high precision, and therefore not things that I will be focusing on in my lectures. You see here some masses, for example, the proton and the neutron mass, the axial charge, which is also something that only involves a single particle state, as well as some renormalized parameters of the theory defined at high energy. So we have this wide range of pre and post dictions, and I just like to zoom in on this one because I think it's so beautiful. This is the strong coupling in the perturbative regime. And so the idea here is we input this very low energy information. This is the mass of the pion, the kaon, the omega baryon. And then there's a numerical method called step scaling by which you can map to higher and higher energies and convert this low energy input into a very high energy output. In this case, the value of the perturbable coupling at the scale of the Z boson. And you can compare this very precise lattice average with a PDG non-lattice average, and you can see they agree quantitatively at a very precise level. And so that means we have overwhelming evidence that QCD is the correct theory of the strong force over an incredible range of energy. It could have been that QCD is very successful in the perturbative regime, But for many years, we didn't have really precise non-perturbative tests. And it could have been that once we got into the precision non-perturbative regime, maybe something would go wrong. Maybe it wasn't the correct theory. But by mapping these inputs into the Z boson regime and seeing quantitative agreement, we have that evidence. So we can say overwhelming evidence for QCD and also evidence for lattice QCD as an effective tool and going forward a tool for new physics searches to start to make precision tests of the standard model using this reliable theory. Now, the final perspective I want to give is lattice QCD in sort of a landscape of different ways of deforming the theory. So we know we have a non-perturbative regularization. We know we have a definition that is well suited to numerical evaluation. And I like to just kind of flash up this landscape where I say, my ultimate goal is to have non-perturbative quantum field theory, to think of all of the different mathematical methods for accessing the properties of the theory without perturbation theory. A subset of that is lattice QFT, the method of putting it on a grid. And a subset of that is lattice QCD, where I say of all the quantum field theories I might want to explore, QCD is one of particular interest. What we will talk about thoroughly in these lectures is the idea of finite volume quantum field theory and indeed imaginary time or Euclidean time. And you can see I've made those bars overlap all the way out to the far right because, of course, I don't have to use a lattice to think about a finite volume field theory. I can think about this in the context of any non-perturbative framework. And finally, you see that numerical lattice QCD sits in this corner. So numerical lattice QCD is necessarily a finite volume imaginary time implementation of lattice QCD, but the finite volume doesn't imply the need for a lattice. And indeed, we're going to see a lot that we will talk about finite volume physics without worrying about the lattice spacing. So what are the limitations of lattice QCD? Well, we know we're evaluating a path integral, and we are using the lattice regularization to set this up for numerical Monte Carlo importance sampling. This sort of represents our dream. This is a cartoon of how we get out our observable by integrating over all quantum fields, weighted according to the exponentiated action, where this is all-important I that represents the oscillatory behavior that leads to correct physical predictions. What we actually do is a bit different, and that's why I've put a question mark here for the observable. I've replaced the I with a minus sign, and I've made here a discrete number of dimensions representing the fact that I am on the lattice. So anytime we do such a calculation, we have to make 3 key modifications. We work with a non-zero lattice spacing, we work in a finite space-time volume, and we work with Euclidean signature. Unfortunately, the stiffness of my t-shirt is just popping the microphone off at regular intervals. I'll try to grab a bit more. And so we really have to think on a case-by-case basis whether these 3 modifications are going to make it impossible for us to access an observable of interest. We shouldn't assume, if you think I'm interested in the proton mass or I'm interested in a proton-neutron scattering amplitude, I shouldn't automatically think somehow lattice QCD will give that to me. I have to prove on a case-by-case basis that it's possible to get that information out, given that I've made these very brutal modifications of putting it on a grid, putting it in a finite space-time volume, and only accessing Euclidean signature quantities. It's also worth mentioning that many lattice calculations work with unphysical masses of the particles, but as most of you will know, that's a problem that's increasingly going away, and now most, if not all, collaborations are at either physical masses or very close to physical masses. And so now I come to this sort of overarching idea of QCD, and perhaps I'll make some mention of QED in a Euclidean finite volume. And the main message I want to give before I go into the details is that sometimes the finite volume is an unwanted artifact. And in those cases, when it's an unwanted artifact, then we extrapolate L to infinity to predict the observable of interest. But the finite volume can also be a useful tool because we can fit data to a predicted L dependence, and that can allow us to uncover observables that we otherwise might not access. Using the volume as a tool, in fact, often resolves the problem of Euclidean signature, and that's what we're going to see in these lectures. And with that, I come to the outline of the whole lecture series. I won't go through all this today. I'll already zoom in on what I'm going to attempt today, so let's not worry about tomorrow for now. The plan for today is to give some warm-up and definitions, to really dive into the meaning of Euclidean versus Minkowski, and a bit the finite volume setup that will be of crucial importance. Then I would like to spend some time on quantities that have exponentially suppressed volume effects that decay as some exponential. And then I want to come to the idea of scattering particles in a lattice calculation. The so-called 2-to-2 scattering formalism that Hartmut already mentioned is due to Martin Lucier. I can already stop and say, are there any questions here before I continue?
Maybe about in the beginning of the we call it at long perturbative renormalizations, we transform the something like coupling constant from the low energy to the high energy. So
yes.
I'm wondering why we try to combine the physics between the low energy and the high energies. So
good. Yes. So the question is, when I talk about predicting something like alpha S, the strong coupling evaluated at a very high energy scale, why is that a worthwhile goal? Why do we chase this program of putting in low energy inputs in order to make a high energy prediction? There are many ways to answer the question, I think. One is that it's now just one of the most precise ways, if not the most precise way, to predict the strong coupling. So the strong coupling is going to be an input to perturbative QCD predictions. The other is that it's just really important to test that QCD gives a correct description of nature over a wide range of energies. And by going from a low energy input to a higher energy output, you're testing that energy dependence and the correct realization of it. Happy to talk about that more. Okay, so let's jump in with some definitions. And now I would like to come to the chalkboard, if I can. I'll just drag it out to the center here. Okay, so the first sort of topic I want to bring to your attention is Euclidean versus Minkowski. Should I adjust some lights somewhere, maybe? I'll let Harvey. Okay, so when we think of Euclidean versus Minkowski, maybe a good starting point is to just think about four vectors, where we're sort of setting up a notation of how we describe position and momentum in a non-relativistic or a relativistic context. So I'm going to be very explicit and give a M label for some Minkowski quantity. So M here stands for Minkowski, and the alpha index represents the fact that it's a four vector where alpha runs from 0 to 3. So then I can split this up into, say, a temporal and a spatial component, working in units where the speed of light is set to 1. And I know I can also do the same kind of thing with the momentum quantity, where I'm looking at the energy component in the momentum component. And then I can, for example, form dot products that define Lorentz invariance. And now here I can, controversially or not, show you the metric that I prefer when I am thinking in Minkowski, which is the mostly plus metric. I'm expecting to hear boos. No, maybe no one has that strong an opinion. So the dot product, I would define it as saying, take the negative product of the energy and time and the positive spatial dot product of P and X. That means write bigger, Felix? Good, I'll write a bit bigger. And when I go to Euclidean instead, all I'm really doing is packaging the information slightly differently. So for one thing, I'm choosing to let the index not run from 0 to 3, but 1 to 4. And I'm choosing to order the information so that I first give the spatial component and then the temporal. And if I reference the t coordinate I have up here, within the Euclidean vector, it enters as I times t, which I might also call tau. And so what we can already see, what is of crucial importance, is that if I know a function for all complex values of t, and I know that function for all complex values of tau, that's equally useful information. So there's sort of two ways to interpret Euclidean. One is it's just a repackaging of the information. The other is if I only know something for real tau, that's a real loss of information if I would rather know it for real t, which would be imaginary tau. So we need to keep in track of that distinction. One is just a notational, and the other is a real loss of information. And then it's worth remembering that when I form a dot product with Euclidean quantities, no minus sign enters. So in this case, I would just have some combination like this. Okay, so having set that up, I now would like to think in some detail about a Minkowski two-point function and a Euclidean two-point function so that we can really compare them side by side and hopefully get a sense of how the information in them is very closely related but not quite the same. So let's start with the Minkowski two-point function. I'm going to define this in momentum space. And so what I would like to do is use a tilde to represent I'm in momentum space, a Fourier transform from position space. And I'm going to be very judicious with these M labels. So it's a Minkowski quantity. It depends on a Minkowski form momentum. And it's defined via an integral over space-time, d4x. I have a phase for the Fourier transform that I'm applying. And then I just have a time-ordered two-point function, vacuum expectation value, of some generic scalar field that I'm going to call phi. And the reason I'm taking some time to look at this is because I want to think about exactly what parts of this depend on the notion of Euclidean versus Minkowski and what parts of this are metric independent, just simply do not carry that label of Euclidean versus Minkowski. How is the visibility of this in the back? Is it OK? Cool. So now I think I will have to rely on other boards. I guess, can I more or less leave this as it is? Is it well visible? Oh, no, I'm activating things. Great. So continuing this line here, the next thing that we want to do is break the time integral up into different regions, because we know this time ordering operator tells me this field should be on the left if t is greater than 0, and it should be on the right if t is less. So let me focus in on the case where t is greater than 0. And therefore, I'm going to integrate from 0 to infinity in the time coordinate. And that allows me to unpack things a little bit more precisely. So now I end up with a simple phase factor involving energy and time. And I end up with one of the time orderings, where I can now also project this field to definite momentum. So it's at 0 time. It's at definite spatial momentum from the spatial momentum Fourier transform. And now I can put in the meaning of Minkowski time inside of the field, which is simply that I have e to the minus iht. And then I have the next field that comes in, and then I come back to the vacuum state. So this is only half of the story. I need another integral where I'm going from minus infinity up to 0. I'm not going to write that one out explicitly. But what we can already see here is that now this field has absolutely no memory of Euclidean versus Minkowski. The same is true for here. It's all built into this evolution operator in the middle. So once you've unpacked things to this level, it's much more straightforward to think about that concept. And the final step I would like to make is to insert a complete set of states here in the middle, which allows me to, and I'm actually going to give an exercise where you fill in some of the details of this problem. So the basic idea, this can be written more precisely, but is that we insert an identity, which is a sum over the complete set of states in this space. And this is a little bit schematic. You can make this a little bit more explicit by thinking about multi-particle states together with the momentum that they might carry. But when you insert that complete set of states, what you can write is that this is equal to, up to a pesky factor of I, an integral, because in fact we have a continuum of possible states in sort of a generic quantum field theory. We have a matrix element squared that I'm going to call Z. It depends on this alpha quantum number as well as the momentum. And so actually maybe to make my notation a little bit more self-consistent, let me remind you here that really my sum over all states would be an integral over the possible continuum, and that would include a momentum label. So I can give my states that generic alpha label together with that momentum label. That's what leads to this quantity. And then we end up here seeing once again the Minkowski p squared together with the center of mass energy of the alpha state, what I might call the mass of the alpha state, and an I epsilon prescription that's needed to make this thing well defined. And so the key messages that I want to give here is that this is a presentation of the Minkowski correlator. This Z factor here has no memory of Euclidean versus Minkowski, nor does this energy of the state, the center of mass energy. And therefore, all the information is really hidden in the definition of this together with the I epsilon prescription. And representing correlators in that explicit way can be a very powerful tool for achieving the relation between a Minkowski and Euclidean concept. So let me now write a similar story for the Euclidean. So I start with a very similar sort of matrix element, except in this case, it's evaluated at a Euclidean form momentum. That means it's defined as a Fourier transform where this p dot x no longer has any relative minus sign. It's just a sum of the components p4 x4 together with p vector x vector. And then the time-ordered object that appears here is now evaluated with a different time ordering, because what we now know is that the time evolution operator in here is no longer e to the minus ht, but now appearing on the right side of the field would be e to the minus h tau in the tau greater than 0 ordering. And again, this is the same Hamiltonian in the two stories. So once we've made things explicit at this level, then we see all the differences between the two. And this finally allows us to, again, I'll let you fill in some steps in an exercise. This allows us to present the result as the absolute value squared of exactly the same matrix element, now weighted according to the Euclidean p squared. And what we finally are able to do here is to think about the complex plane of these quantities. And so I would just like to draw a sketch of that and then show some slides that will summarize the message further. So here's the Minkowski side, here's the Euclidean side. And the final comment that we can make is, if I look in the complex plane, I'll just squeeze it in here. I can think at fixed p vector, this will be a sum of p0. So in fact, let me set p vector equal to 0 now. And that leaves me with the complex p0 plane. It looks something like this. So the idea here is that this represents real energies, real p0. This represents complex energies, complex p0. And I've set p vector to 0. Similarly, down here, I want to set p vector to 0. So I'm left only with the dependence on p4 sitting inside of this. And so I'll have a second complex plane, which depends on that p4 coordinate. And now what I can see is that there's different singularities that can appear that come from these expressions. So in this case, what I see is that due to the metric I've chosen, this pm squared actually becomes minus p0 squared. And that means that I hit some kind of singularity whenever p0 squared is equal to m alpha squared. One possibility is that when I'm summing and integrating over the alphas that represent all possible states, maybe I have some isolated state in my system, a single bound particle that's just sitting by itself. That would lead to a pole. And I'm going to put that pole slightly below the real axis because of this I epsilon prescription. And because this is a function of p0 squared in the complex p0 plane, you see that there's this sort of reflective property. These exact same poles live in the p4 plane on the imaginary axis, just right smack dab above and below on the imaginary axis. And the continuum of states that I have here, once I maybe go above the single pole, those are going to lead to other structures, generically branch cuts. So now you can imagine there's some branch cut running off to the left here. There's some branch cut running off to the right here. And those same kind of branch cuts exist here, running down the imaginary axis and running up the imaginary axis. And so we've seen for the final time, the exact same physical information is packaged in these two correlators. In the Minkowski correlator, it's packaged in terms of these matrix elements and energies that manifest as singularities infinitesimally above and below the real p-naught axis. The exact same information lives in the Euclidean correlator along the imaginary axis, where the pole positions and the branch cuts and the discontinuities, all of the details are the same. They're just living in a different part of the complex plane. So if I would know this Euclidean correlator everywhere, I would have perfect knowledge of the theory. If I would know this Minkowski correlator everywhere, I would again have perfect knowledge of the theory. The problem comes if I only know, say, on the real axis, and then I have to struggle to go into the complex plane. And we'll see that on the slides as well. So let me go back to the slides and let me ask again, are there any questions on this chalkboard presentation before I continue? Good. So to say it in different words, whenever we're asked, is something Euclidean or Minkowski, the first thing that we should always think is the question well posed? And sometimes it is. So certainly for correlation functions or for four vectors or for the quantum field theoretic path integral itself, it's meaningful to ask, is the thing Euclidean or Minkowski? However, if you're talking about the Hamiltonian itself, or masses or, say, decay constants, as well as what we'll talk about at great length, finite volume energies, these things are not meaningfully Euclidean or Minkowski. There's just a unique definition for each of these things that doesn't carry that label. The same is true for scattering amplitudes, local matrix elements, and something I might mention at the very end, which is spectral densities. For the case of correlation functions, Minkowski versus Euclidean is important when we have limited knowledge. For example, if we just have some numerical estimate for real Euclidean momenta, but it's irrelevant whenever we have full analytic knowledge. And just to hit the point home, I can show this example of, suppose the Euclidean correlator was a tanh function. So here's the tanh function. And now I'm plotting the real part of my Euclidean correlator for all real Euclidean x and for all imaginary Euclidean x. This is what tanh looks like in the complex plane. And I have complete analytic knowledge. Analytic continuation would give me the Minkowski correlator, which is not tanh, but tangent, up to and over all I. And I could plot my Minkowski correlator again. And you can see I've taken the same sheet and just rotated it a bit. So it's just a relabeling of the same information. Suppose, however, the Euclidean correlator is the tanh function, but I don't know that. I don't have that analytic knowledge. All I have is some noisy numerical data for real x. And now the problem is that it's very challenging. So I've basically sliced it along this direction. I don't see those poles directly, and that's where I'm in trouble. Now the analytic continuation actually is ill-conditioned due to this noisy data, and that's where lattice QCD faces a problem. Because I only have that noisy data, and if I want some Minkowski information, I'm going to have to be clever and work hard. And so just to summarize one final message, correlators where the Minkowski versus Euclidean label is meaningful are often used to access observables where the label is not meaningful, and that's what we're going to do extensively in this lecture. And that brings me now to the finite volume setup. So okay, we've really had a look at Minkowski versus Euclidean and what it means, and now I want to come to the other big topic of a lattice field theory, which is the fact that it's in a finite space-time volume. And what's very important for this talk is to think, if I'm in a cubic spatial volume where I have extent L in each of the three spatial directions, and there's different ways to put your system into a finite volume, but this is the one that I'm going to focus on primarily. We have periodic boundary conditions, which means the quark fields are subject to this periodicity, that if I have some quark field at tau and x, if I shift by a step L in any of the spatial directions, that the quark field must take on the same value. It satisfies that periodicity. And the low energy degrees of freedom of the theory, say the pions or the protons or the neutrons, they inherit that same periodicity. For much of what I discuss here, we're actually going to approximate the time direction to be infinite, meaning we're going to expect the numerical analysis of the data to remove the finite temporal extent effects, so that you can think of the data as coming out with an infinite time direction. And we're also often going to think in the continuum, we're going to assume that the lattice spacing effects have been removed. We will briefly consider finite T effects and maybe lattice spacing effects tomorrow. So what does it mean that my pion fields satisfy the periodicity? Well, what it means is if I think of the relation between position and momentum space, I know that the position space pion is equal to an integral over my cube of the momentum. No, this is actually the wrong way around, these labels. Okay, but this final statement is true. I think I have to relabel this slide. This should be an x and this should be a p. So you're Fourier transforming from x to p, and you know if you shift by a step L, then it must be true that you get the same result. And a consequence of that is that this phase factor, e to the IP multiplying the box length, that should equal 1. Because for this periodicity to hold for all field configurations, it must be true that that phase is just 1. And that means that the thing sitting up in the exponent must be a multiple of 2 pi. So what we conclude is that our momentum component times L should be some integer multiple of 2 pi. And this is why periodic finite volume effects imply quantization of momentum. So whenever our fields are in a periodic box, the momentum, spatial momentum, is going to be an integer vector multiple of 2 pi divided by the box size L. Any questions about this one? Because it'll be used quite a bit. Yeah. Yes, so there is a typo here. I'll fix it when I upload the slides to integral. So the problem is that this is shown as a function of x, but here there's an integral over x. So this is wrong. So this should really be a sum over the p modes. And then when you have a shift, you would have again here the sum over p modes. But the fact that this bit has to be the same is true. So it's still true that this just has to equal 1, which leads to the quantization of momenta. Sorry about that. So we've realized that momentum is quantized, and now we can think a little bit more critically about the Fourier transform. Beginning in the infinite volume world, how do we set up our convention for a Fourier transform? Well, what we say is I have some function f. I want to define the Fourier transform on f, and I want the property that if I apply the Fourier transform and then I apply the inverse Fourier transform, I get back to where I started. So here now things are written correctly. I have some function f of x prime. I go from x prime to p. So now the thing in the square brackets there is a function of p. And then I apply a second time to go from p back to x. And I insist that this just gives me back f. And the reason I'm showing this is because I want to think a little bit about how things are normalized. So this capital N and capital N prime, they represent some normalization convention. And what we can see is that I end up with the integral of the phase. So if I put together the IPX and the minus IPX prime, I can do the p integral and I just get a Dirac delta function relating x and x prime. So that's why the Fourier transform in its inverse is so straightforward. It's because it's related to this Dirac delta function. But of course I have this pesky 2 pi. And so what I conclude is that 2 pi gets divided by these normalization factors, and I can choose what value do I want to assign to the normalization. Sometimes people would say maybe I make each one square root of 2 pi, but in quantum field theory, the standard is to set this one to be 1. So to say when I go from position space to momentum space, I just don't have any normalization factor, and whenever I have this momentum integral, there I put the 2 pi. So that's a convention that we establish, and that's why this is the canonical Fourier transform setup in a quantum field theory. Just the simple integral of dx prime takes me from position space to momentum space, and the integral with dp over 2 pi takes me back. So now I want to do the same game in a finite volume. So now I say, well, my f of x prime only lives in this finite extent between 0 and L. So I'm going to do my position space integral between 0 and L. And I'm going to already put in the fact that the momentum I have is some integer multiple of 2 pi over L. So that's in the square brackets going from, again, position to momentum. And now I can use a sum over all the allowed momentum modes. That replaces the dp integral, and that takes me from momentum back to position. And once again, I have an unknown normalization. And now something funny happened with the projection. Oh, now it's okay. It's very similar. Instead of having the integral identity for the Dirac delta function, we have this identity, that if you have a sum over all plane waves with a 2 pi periodicity, this is something that we often call a Dirac comb. It's equal to a set of Dirac delta functions. And so I group together my phase factors, and I do the sum, and I see I end up with this Dirac comb. And I see that only one Dirac peak appears between 0 and L. So when I do the integral from 0 to L, I just get a 1 from that single peak. And so what it all boils down to is the fact that just as here I had 2 pi over the normalization factors, here what I end up with is the box size L over the same normalization factors. And so I have to choose somehow where to put the L in my normalization. And just as I said, well, let me make the dx integral just a simple one, I do the same thing here. I say let the dx be simple, and let me put all my normalization factors when I'm thinking in the momentum space side. And so this is the final message. The standard for the infinite volume Fourier transform is a simple x prime integral and a dp over 2 pi on your way back. The convention in the finite volume world is a simple x prime integral over the finite volume extent, and then a 1 over L multiplying the momentum sum is the standard way to go back from momentum space back to position space. So you can see them there side by side. And as a sanity check on this, we can imagine taking the infinite volume limit. So we can say, what if I have some function, f of p, and I'm summing it over the modes, and I'm using my 1 over L factor that I decided was the correct way to do that. What you'll see is when you send L to infinity, the function is evaluated at 2 pi over L times all of the integers. And if f is some nice smooth function, when I'm sending L to infinity, that means the sum is running over points that are very close to each other. So the idea is that the sum over n can be replaced with an integral over n for a smooth function. And you end up with exactly the 1 over L out front and the integral over n where the function is evaluated at 2 pi n over L. Then you just do a simple change of integration coordinate, and you see that indeed your limit transforms exactly to the integral with dp over 2 pi. And so we see everything makes sense because we have a convention in the infinite volume, a convention in the finite volume, and we see that if you send L to infinity, the difference between the sum of momentum with 1 over L minus the integral of momentum with the 2 pi, that difference exactly cancels in the limit, and we see that the sum minus integral goes to 0. So this is a little bit of a setting up convention, but it's going to be very important when we're doing derivations in the finite volume going forward. Any questions about the basic setup of this slide? Yeah, please. Yes, absolutely. Thank you for asking. Yeah, that's actually a very good idea. Yeah. I'll try to be careful.
Is it possible you could explain one of those earlier slides that I'm sorry that I could not understand? So the one when you switch from the blackboard to this one, you mentioned that if we have something in the Minkowski and if the description you have to find it, that part I could not get. I'm sorry.
Yeah, absolutely. Thank you for asking. Was it this one?
The earlier one actually.
Did it have the pictures? Was
Yes,
it this one?
right.
Yeah, very good. Right, so the idea, I was doing an analogy where I would say, imagine my Euclidean correlator is just the function tanh. Now we know tanh as an analytic function. I can, for example, plot it using Mathematica as I've done here. And if I would know for all real and imaginary coordinates the function, then I would just have complete knowledge of it. So the only problem is when I say I only know the function along this black curve, then I might be in trouble. But again, if I would know the function analytically along this black curve, I could use analytic continuation to map out the entire complex plane, and once again I would have perfect knowledge. So I really only run into trouble when there are two things happening. One is I only know the function along this curve, and two is I only know it maybe at discrete samples and maybe with some statistical uncertainties. So I'm sort of telling you a lot of bad news. One, I only know the function in a limited region. 2, I only know the function at discretely sampled points, and 3, I have statistical uncertainties. And those 3 things together mean a true loss of information, that if I then want to reconstruct exactly where these poles are, it's going to be very hard to do in practice. So that's why Euclidean is a problem in this example, in this analogy, and in general, it's a problem when you have limited access to the complex plane, discrete sampling, and statistical uncertainties. And that's the idea.
And so I used to confirm the last relation that you proved between the finite volume and the infinite volume. That is only for periodic boundary conditions.
That's right. So this setup is assuming that your function f has periodic boundary conditions. In fact, one of the exercises will be thinking about some other boundary conditions that let you explore that freedom a bit more. Okay, so I've said everything I want to say about the meaning of Euclidean versus Minkowski and about the basics of the finite volume setup. And now I want to actually come to calculating some finite volume effects, starting with those that decay exponentially, because we'll see that's actually very instructive for the scattering that we're going to get to down the road. So I think I will use the same board and continue in that way. So let's think of what is sort of the simplest way that we can start to think about finite volume effects quantitatively. And I think the answer is in perturbative scalar quantum field theory, and in particular in perturbative phi-4 theory. So that's what we're going to think about for the next minutes. And maybe because people tend to read left to right, I'll actually start on this board this time. So what we need to do here is remind ourselves how we set up a scalar phi-4 theory. In particular, how do we set up the Feynman rules? Then we're going to use those Feynman rules to calculate the mass in the finite volume context. And then we're going to manipulate those expressions and see quantitatively the exponentially suppressed effects of the mass. So here we go. Particle mass in lambda phi-4. So the things that we need to remember are that when we write down the Lagrangian for lambda phi-4 theory, we just end up with 2 building blocks for our Feynman diagrams, which are a propagator and a single vertex. So this is what we're going to use. The propagator, I'm going to think with a Minkowski convention, and with the mostly plus, I'm going to write that as 1 over p squared plus m squared minus I epsilon. This is the Minkowski mostly plus convention. If you haven't seen it before, Mark Shrednicki's QFT book, for example, uses this convention. I see some concerned faces. If you want this to be p squared minus m squared, come talk to me about it at lunch, because both are correct as long as you keep track of your conventions. And then I have the vertex, which is just minus I times the coupling. Now what I'm doing here is using Baire parameters. So these are the Baire parameters in the Lagrangian, and we'll take care of that down the road. So now how do we think about the mass of the theory? Well, we remind ourselves that when I'm thinking about the mass squared as it relates to the parameters of the theory, what I do is I think in terms of the self-energy diagrams. And so what's true also in the infinite volume context is that the physical mass is equal to the Baire mass together with a sum of all diagrams. And at leading order, the only diagram that I have to worry about is this one. And this will continue at order lambda squared. So the idea is I need to draw all diagrams that have exactly 2 external legs and any number of loops as I please. And this will represent order by order the relation between the physical mass and the parameters of the Lagrangian. In this case, I'm doing all that in the finite volume world. So I've already set that up. And now I just need to remember what this diagram means mathematically and just evaluate from there. So all it means mathematically if I now zoom in on this by itself, is, well, I have a factor of the coupling here. That just comes from that vertex. I have a factor of I from the propagator. I have the fact that I have a loop means I get an integral over the temporal component of momentum. And the fact that I'm in a finite volume means that I get a sum over the discrete momentum modes that are required by the periodicity. And then I'm already going to write out the propagator in a little bit more detail. In my convention, it's minus k naught squared plus k vector squared plus m naught squared minus I epsilon. And this is almost the whole story. Can anyone see what I'm missing from my expression for the Feynman diagram here? There's a simple factor that I messed up. It's a loop, which means I can swap it around on itself. So what am I missing? Exactly, just this combinatoric symmetry factor. Just a factor of 2 here. Exactly. Good. So there's a couple of important points here. First is that I'm just remembering the rules of perturbation theory. And second is that the only thing that's different from the perturbation theory that you have learned in any textbook is the fact that whenever I have a loop, instead of just doing a 4-dimensional integral, I do an integral over the temporal component and a sum over the spatial component. And that's all it means to do finite volume perturbation theory. So now that you know this new rule, you can evaluate any Feynman diagram you've ever heard of in a finite volume simply by putting in these sums everywhere. So actually the rule is remarkably straightforward, that you just make that simple replacement. Then of course it's the question how straightforward it is to evaluate the formulas. The fact that this is still an integral is because we're approximating the temporal extent to still be infinite. So if we wanted to worry about the finite time effects, we could modify this as well. But in practice, it's very useful to think in this framework, to say, let's assume the lattice data has removed the finite temporal effects, and I really want to think about the finite spatial effects, which are often more important, and this diagram represents that. And now I just evaluate. So now that I've made this thing explicit, one thing I can do is just a simple Wick rotation that goes from k0 to k4. So I'm sort of going back to Euclidean, but I'm just doing it at the level of an equal mathematical expression. So this is just exactly equal to this simpler version where I have lambda naught over 2. I have the k4 integral now. The sum just comes along for the ride, completely unaffected. And now I don't have to worry about the I epsilon prescription anymore because I just have k4 squared plus k vector squared together with the mass. And I just want to really emphasize that these two lines are just exactly equal to each other. So that's a case where Euclidean versus Minkowski doesn't matter because the mass itself doesn't carry the label of Euclidean versus Minkowski. So it can be equally well represented with this expression, with that expression. They're just mathematically equivalent. And now I can use a trick that already appeared on the slide where I say, if ever I have a sum over delta functions, that's the same as a sum over phases. Or if I have a sum over phases, that's the same as a sum over delta functions. What that means here is I can represent the sum over k as an integral over k together with this Poisson sum. So let me do that now. I'm just going to rewrite this as the lambda over 2, and now a sum over some integer vectors n. And now I'm actually allowed to do the 4-dimensional Euclidean momentum integral because this phase that I'm writing here is taking care of the sum. And so if you stare at this expression, what you'll see is when you combine this sum over n with this phase here, it will just lead to a sum of delta functions. And when you hit that sum of delta functions with the integral, you'll exactly get back the sum of k vectors that you had. So it's just a nice trick to rewrite a sum of k vectors using the Poisson summation formula. And then finally, this propagator comes along for the ride. But to make faster progress, I'm already going to write the propagator in a slightly different way using a Schwinger parameter, I'm going to add an integral d alpha, and I'm going to write e to the minus alpha m squared plus k Euclidean squared. You can see if I evaluate this integral in alpha, I'll just get a 1 over m squared plus k squared out front. So this is just equivalent representation. And this is what I can now continue on this side of the board. The final step that I want to do is to separate out the fact that this is a finite volume diagram, and if you want, it's represented with a sum over the momentum that are allowed in the finite volume. I want to replace that with a version of the diagram that lives in the infinite volume world and therefore has an integral. Shown here. So how do I make sense of that? Yes, question.
Exponential, you have m vector times the ke, which is a 4 vector, like one line above. How is that?
Yeah. Yeah, good. In fact, there's a slight typo here. Good. So what this means is I want to define n as a 4 vector to just be a 3 vector together with a 0 in the temporal part. And that's just a way that lets me represent. I could have also done a 3 vector product here. So this is what I really have in mind. This sum, what it means is freeze the temporal part to 0 and just sum over the spatial parts. But I just want to use the 4 vectory notation. So I just promote this to a 4 vector with an empty temporal component. Great question. Thanks. So let's see here. I have this expression, and it represents the sum over all the momentum modes. And now I want to say, if this were integrated, that would be the same diagram in the infinite volume. So I would like to somehow connect the sum one to the integrated one. It turns out I can do it here by focusing in when n is equal to 0. Because if I set n equal to 0, that just sets this phase factor to 0. And then you can, or it sets the phase factor to 1, excuse me. And then you see you have exactly the coupling, the d4k integral, and this would become 1 over k squared plus m squared. So there's many reasons why this Poisson representation is useful, but one thing that's super useful is by setting n equals 0, I separate out the infinite volume part, and that means what's left over, which is the difference between the finite volume sum that I started with as compared to the infinite volume integral. The difference between them is given by the same sum where I exclude n equals 0. So now I can just copy this down. Lambda naught over 2, the sum where you don't include the 0 vector, and everything else is the same. Maybe I'll just write it one more time so I'm not doing too many things at once. d4ke over 2 pi to the 4th, the e to the I L n dot ke, and then this Schwinger parameterization of the propagator e to the minus alpha k squared plus m squared. Great. And so now the only thing that's left to do is evaluate the k integral. And because I just have a nice Gaussian here, I can just group things together to evaluate that Gaussian. And so I end up with this expression. I end up getting some powers of m coming from the dimensionality of this d4k integral. If I group together the various powers of 2 and pi, I end up with a 32 pi squared. And I continue to have, now I'm going to write it really in terms of the spatial 3 vectors. So I'm going to stop using this 4 vector notation here. And I still have not done the alpha integral. So that's the one that I still will have to worry about. And this is a very instructive result because it shows us that this expression would actually be divergent if this term weren't here. So imagine if I set n vector to 0, then this whole thing is absent. Then I here just have a simple exponential e to the minus alpha. But if I'm integrating alpha down to 0 and I have a 1 over alpha squared out front, then I'm just hitting a 1 over alpha squared divergence as alpha goes to 0. So this would just be a divergent integral. And indeed, it's true that the infinite volume integral by itself is UV divergent. So normally when I think about this, I would have to say, I'm going to use some regularization. Maybe I use dimensional regularization. I'm going to use a scheme like MS bar, where I subtract the divergences into the counter terms. But I avoid those issues here if I just say, I'm only interested in the difference between the sum and the integral. Because in that difference, this n is guaranteed to be non-zero, which means I always have this term here. And as alpha goes tiny, this is creating some 1 over alpha squared divergence. But this e to the minus inverse alpha is creating an essential singularity that damps off that divergence. So this is a perfectly safe integral. You can evaluate it completely. And in fact, it's just a particular modified Bessel function. So you can just look up what it is. And so the punchline becomes, if I take the mass in a finite volume minus the mass in an infinite volume, and I divide that by the mass squared, I just end up with this coupling over this 32 pi squared, a sum over all of the vectors of the theory of this Bessel function k1, which depends on m times L times the momentum mode. And this is the final result. And I can also use the fact that for a very large argument, this Bessel function decays exponentially, and I can use its asymptotic form to give one more expression. And in this case, I'm only going to keep the dominant parts of the sum. Since this is decaying exponentially, it's dominated when its argument is small, and the argument is small when this vector has magnitude 1. So there's 6 ways for a 3 vector to have magnitude 1, which are 0, 0, 1, 0, 0, minus 1, etc. So I get those 6 nearest Poisson modes. And then I just copy down the expression that comes from looking up the asymptotic form of the Bessel. And then there's higher order terms that I'm neglecting. Good. So this is the main result we wanted to arrive at. So the key lessons that we can take from this result are, I can always use perturbation theory to study finite volume quantities. The general recipe of doing that is to represent your Feynman diagram using a sum rather than an integral. It's then almost always very useful to rewrite that sum as a sum over Poisson modes, and to separate out the 0 Poisson mode, which is the same as separating out the infinite volume integrated diagram from the finite volume sum diagram. The difference between the two is then almost always a nice finite quantity. You can see the finiteness coming from this 1 over alpha in the exponential. And when it evaluates to this simple Bessel, we conclude that we have exponentially suppressed volume effects. And it happens to be true for all particle masses in QCD and for all single hadron matrix elements that we have these exponentially suppressed volume effects. So let me show that same expression up here now and just make one more comment. So here I just want to show this is the same result. Now you've made a little bit more explicitly the terms that we've dropped. So the leading term is this known geometric factor, depends on the coupling of the theory itself, and it holds up to higher powers of 1 over L as well as higher exponentials. So you still have to have your box size big enough that you're dominated by this term. The final comment I would make here is that to the order we work, this coupling would just be the same as the 2 to 2 scattering amplitude evaluated at threshold. So this is actually the first time that we're seeing a hint that there's a relation between finite volume effects and scattering quantities. We've concluded that there's this universal geometric factor, but the exact size of the volume effect you would see is also determined by the scattering of this particle. So for example, that's a hint that even if you would just have the single pion in your lattice calculation, and you would measure the pion for a bunch of different box sizes, if you could really resolve the exponential dependence, you could do a fit, and the prefactor would in fact tell you something about how pion's scattering. And so I already said at the beginning, the finite volume can be useful because we can use the L dependence, we can fit it to known formulas to extract information of the theory. And this is the first example of that. And I also thought it was interesting to make this plot here. So the orange curve here is the full result at order lambda, and the green curve is the approximation we've done of just the leading exponential. So those agree quite well. If you want, this is the volume effect in the case when the coupling would be set to 1. And you can see it's very much smaller than a simple e to the minus ml. So the lesson that I would give here is, if you're thinking, are my volume effects big and small, don't just think e to the minus ml is the whole story, because the details of this formula can make a difference at the level of many orders of magnitude. And also the interaction strength matters a lot. So if I make my interactions stronger and stronger, the volume effects will get bigger, and that will determine the extent to which they matter. Very good. So I think this is all I would say about exponentially suppressed volume effects, because I do want to get into scattering. Any questions about that before I continue?
I was wondering, has anybody ever done that? What you meant, like looking at the finite volume effects of the pion mass and extracted like scattering, I don't know, whatever parameter?
Yeah, it's a great question. So for the pion, I think no. It turns out that Martin Lucier actually derived the full non-perturbative formula of this. And so you can really work out what is the full coefficient that appears here. And it turns out it's not such a simple scattering amplitude. It's a scattering amplitude integrated on some contour in the complex plane. So it's not quite as useful as we might have hoped. There's something very close, though, that is interesting, which is this expression here assumes you only have a 4-leg vertex. And you can also imagine a theory where you have 3 legs instead of 4, like a phi cubed theory. I actually was going to present that, but I think I'll skip it for now. Maybe I'll do it tomorrow. If instead of having a 4-leg vertex, you have a 3-leg vertex, then you get a different exponential here. Instead of e to the minus ml, it's e to the minus square root 3 over 4 ml. So there's this funny square root of 3/4. And square root of 3/4 is a little bit less than 1. So it makes it a dominant exponential. So there's this cute observation that whenever your theory has some 1 to 2 coupling, that you'll get an even more dominant exponential. And that is a case where people have fitted to data in the context of glue balls. So if you're thinking about, you just look at a single glue ball in a Yang-Mills theory, you can ask the question, what is the box size dependence of my single glue ball ground state? And it's dictated by this e to the minus square root 3/4 ml. And the coefficient is the glue ball trilinear coupling. So that's a very similar case where by studying the volume dependence of the glue ball, you can try to make a prediction of the trilinear coupling. And we had the idea to do this and then discovered that Philippe de Faucrand had already done it many years ago. So it's a bit of a hot topic because also there's this S-matrix bootstrap community, and they have some constraints for this glue ball trilinear coupling. So there's some idea that you get the S-matrix prediction. From the lattice calculation, you get the volume dependence of the glue ball. Those are 2 different predictions of the trilinear coupling, and you can compare them. So I do think that's an interesting direction. Maybe here as well, but no one has tried it to my knowledge. Great question.
Yeah, sorry, maybe I missed something, but you're still expanding in lambda, right? And
Yes.
So, maybe like at higher lambda, then coupling can, for strong coupling, then I guess the terms can get dominating, and I guess.
That's right, yeah. So there's a way to, this is just a perturbative result, but there's a way to reproduce this analysis summing all diagrams to all orders. That there's some delicacy that's not a true non-perturbative result, but it's a result that comes from thinking of, let me think of my pions are the low energy degrees of freedom. Let me imagine I have some effective theory with the pions represented by the propagators, and let me sum all diagrams to all orders in the theory. That's what Martin Lucier did. So that's an almost non-perturbative prediction for the leading behavior. But yeah, I'll mention it again tomorrow, actually. Okay, so I've given myself a check mark for the phi cubed theory, but I am not going to do that now because I want to get a bit into the 2 to 2. So We've thought a lot about single particle states, for example, particle masses. We've thought a lot about the meaning of Euclidean, Minkowski, and finite volume, and we've done a calculation where we've already seen how a volume dependence is related to some kind of interaction, in this case a coupling. Now we want to take that farther by thinking of multi-hadron scattering. And I want to just give one slide of motivation. Just let me say that there's been an explosion of discoveries of multi-hadron observables, often in the case of what we call resonances. So if we see some bump in some experimental data, we often interpret this as a short-lived excitation, a short-lived resonance that then decays into the hadrons that hit the detector. And there's been discussion about exotics, XYZ states, as well as tetra and petroquark candidates. These are interesting in their own right. To more fundamentally understand QCD, we want to understand these resonances. But they're also interesting because they affect electroweak processes. So for example, LHCb has looked at these decays of the D meson, and they've found CP violation in those decays. And there's actually a lot of discussion if that is the expected CP violation of the standard model or if it's larger than expected. And a really important message is that you need a method that understands all of the resonances that would be involved. And I think most methods today haven't done that, so we just simply don't know what's the correct standard model prediction. So the reason that we care about multi-hadron observables and about scattering and about spectroscopy is because we've seen these resonances, we know they affect also the electroweak sector, and we also know that we can't think of them as states. So if you have something like a X3872 or a rho resonance or a F0 resonance, it's not actually a state. So then we have to ask the question, what is it? And to think about that, we take a step back and we think, well, at low energies, QCD is built from hadronic degrees of freedom, like pions and kaons. And we can rigorously define multi-particle states. So let me define a 2-pion state, for example. This is an eigenstate of the Hamiltonian. It's a rigorous state in the Hilbert space. And if I build some incoming 2-pion state and I build some outgoing 2-pion state, by forming the overlap, I can define what's called the scattering matrix. And you see, here's my little cartoon for the scattering matrix. It's always going to depend on the center of mass energy. And it's also going to depend on various angular variables. In the case where I only have 2 particles, there's just a single angle, and I can do a projection of that angle onto a spherical harmonic or a Legendre polynomial, and that is what we call projecting to definite angular momentum. So by projecting onto definite angular momentum, I end up with a matrix that is just populated with these simple functions of the center of mass energy. We call Mandelstam S the squared center of mass energy. And in fact, it's diagonal in this basis. And because it's a unitary matrix, because S times S dagger is 1, not only is it diagonal, but the diagonals are just populated with simple phases. So this is kind of scattering 101, that I can build multi-hadron states. I can populate the matrix, in this case, with simple phases. And each of them is a function of S that tells me rich information about how pions are scattering in that partial wave. If I keep going, as Hartmut mentioned, a big part of this program tomorrow will be going beyond the 2-particle frontier, then you can imagine this becomes an enormous space of information. You can imagine building the whole QCD-S matrix with the scattering of all kinds of pions, protons, neutrons, 2-particle states, 3-particle states, 4-particle states, all the way up to scattering carbon-12. So there's a massive landscape here that we can try to understand. And the first statement is just to say, this is a rigorous observable of QCD, and we want to try to get it. Once we've defined it, then we can also define what a resonance is. Roughly speaking, a resonance is just a bump in the scattering rate. And so you can see there's already a nice interplay of things here. There's something called the scattering amplitude that will be very important, which is slightly different than the S matrix. As you can see here, the scattering amplitude is just the S matrix minus 1. And that minus 1 is just removing a disconnected event where the particles fly through each other. And what we can see here is that when you've taken that subtraction, the magnitude squared, which is a rate of scattering, is then just going to be proportional to a sine function. And because a sine function for real arguments has a maximum value of 1, what this tells us is that the scattering rate has a maximum allowed value. And people often say it's the maximum allowed by unitarity, which just means the fact that m is s minus 1 and therefore is a sine function, that means it has a maximum allowed value. And when you scatter pions in experiment, you see, in fact, that value is saturated. So here the energy is being swept, and when the energy is something around 700 MeV, you hit that maximum allowed value. And we interpret that as the two pions forming a short-lived excitation, which is called the rho resonance. And to make that a little bit more rigorous, if I take that same curve and I think of it as a mathematical quantity, I can go into the complex plane and I discover that there's a pole off of the real axis. And so the other message to give is really what a resonance is a pole in the complex plane. And this bridges the conceptual gap between a bound state and a resonance. So a bound state is a pole on the real axis, a resonance is a pole off of the real axis. And in fact, as we vary the quark masses, these poles move around, and they can even move from the complex plane onto the real axis. So now I want to think harder about analytic continuation. And I want to acknowledge that I did kind of a funny thing here, which was I continued the magnitude of m squared into the complex plane. If you look at my cartoon here, it's magnitude of m squared. It's much more standard to think about m itself. So let me think about m itself, and let me ask the question, if I want to analytically continue it, what structure does it have? Does it have any poles? Does it have anything more complicated than poles? And it turns out it has branch cuts. And we can see that in many different ways. So one way we can see it is something called the optical theorem. And the optical theorem is something you'll see in non-relativistic quantum mechanics or in quantum field theory. It just tells you that the magnitude squared of your amplitude is proportional to the imaginary part of the amplitude itself. And the relation between them is this geometric factor, this so-called phase space factor, which involves a square root with s inside of the square root. Rho is this two-particle phase space. If I want to solve this equation, all I do is divide both sides by a magnitude of m squared, and it just tells me that the imaginary part of 1 over m star is rho. So let me say that one more time. Divide this over. It's real, so I can put it inside of here. It just becomes the imaginary part of 1 over m star. And that means the unique solution to this is that the scattering amplitude itself must equal 1 over some real quantity that we call a K matrix, some unknown real short distance thing, minus I rho, where rho is this known phase space cut, this known function. And so the key message is, the scattering amplitude has a square root style branch cut. So if you think of the function square root of x, if you're plotting square root of x for different complex numbers, you'll see that somewhere there's going to be a rip in the function. And that's what we call the branch cut. And every two-particle scattering amplitude has exactly that kind of branch cut inside of it. You'll recall that I drew the branch cuts when we were thinking of Euclidean and Minkowski correlators. So here's that same cut appearing in a different way. Now the final thing I want to do is present the same thing diagrammatically. And it's going to be this is the first time we're going to think of diagrams to all orders. And this is really going to let us understand all of these derivations of finite volume scattering. So it's going to be worth the effort. The all orders diagrammatic expansion, also known as the Bethe-Salpeter equation. Maybe before I do that, I should ask, what's the vision for my time control? Should I go up to the half hour, or should I stop? It's OK. Go up to the half hour.
I think as long as you respect the coffee break.
Yes, the sacred coffee break. Good. OK. Then I will go for another 9 minutes. But I'll ask again, are there any questions about this statement here? The sort of scattering basics.
Why the K matrix includes the short distance and the include the long distance information?
Yeah, that's a very good question. So what do I mean by short and long distance? Well, what I really mean here is that if I draw a Feynman diagram with pions inside of the diagram, I can represent that as integrals over momenta, or I could also rewrite that diagram as a function of positions. And I could break the diagram into the integrals where things are close to each other and integrals where things are far from each other. And I would see that there's a correspondence between the different parts of the integrals in these two things. In momentum space, what that means is when I'm very close to the pole, that's when I am thinking of long distance effects. So this comes from the poles in the diagrams, and this comes from when I'm far away from the poles. And that's the separation of short versus long distance. Okay, So now we want to do the same game diagrammatically. So what we say is, let me just represent the scattering amplitude as the sum of all diagrams. So I'm thinking of, let's say, pion scattering here. So I imagine I have some general theory where something like chiral perturbation theory, but I don't worry about any of the details. I just say each of these lines represents a pion, and these different vertices represent the way the pions can interact. And I just try to draw every possible diagram I can think of. So you just imagine going crazy with that. You start by saying maybe there's a vertex with 4 external legs. Now with pions in QCD, actually you wouldn't have an odd number of legs. But as a general rule, let me also just play the game for an odd number of legs. So this could be describing other theories as well. Let me draw all diagrams that have 5 external legs, also, or with vertices that have 5 external legs, and just keep going. So really imagine you play the game where you just draw every possible diagram. And now the claim I want to make is this infinite sum of all possible diagrams can be represented in this very simple series where I just have blue blobs, and then I have any number of 2 pions propagating along between the 2 blobs. So somehow it's true that all possible diagrams, all possible topologies, can be represented with this simple series. Sometimes we call it a ladder series. And so you can ask yourself, well, how could that be true? And one way to phrase it is come up with a definition of the blue blob and the red dotted line such that it is true. And so that's what we're going to do. So we'll say, OK, this first diagram has to be accommodated somewhere. And since it clearly doesn't have 2 pions propagating in the middle, it can only be accommodated if it's just inside of this blue blob. And this is what's going to be called the beta-Salpeter kernel. So what I'm telling you now is that simple contact that must be inside of the beta-Salpeter kernel. When I come to the next diagram, I say, now this is already taken care of because I have 2 of those 4-point vertices. So those are each covered by that contact inside of the beta-Salpeter kernel. And just by saying that this red dotted line has to contain the simple propagator, I've covered that completely. Those ones, again, there's never 2 pions propagating along. So I just say U must be inside of the beta-Salpeter kernel. And now these are sort of the most complicated ones. So the way these get accommodated, I say, let's study this one. This thing on the left must be in some beta-Salpeter kernel. This on the right must be in some beta-Salpeter kernel. This decoration in the middle, it can only be accommodated if I say it's part of the red dotted line. And so you can see, just by insisting that the red dotted line also has that decoration, I've accommodated these kinds of graphs. And you can continue this game all the way along. And so the conclusion is that the sum of all possible diagrams is exactly equal to this lattice series, provided that the beta-Salpeter kernel contains all diagrams that are 2-particle irreducible in the S channel. So that means it contains almost all diagrams. But if you have a diagram where only 2 pions are propagating, don't put it in here because it's already counted up here. And then the red dotted line is simply the fully dressed propagator. So the beta-Salpeter equation lets you rewrite all possible Feynman diagrams in this ladder series up to those 2 caveats. So why is that useful? The reason it's useful is because the beta-Salpeter kernel is a smooth, real function at low energies. Maybe I will give more details on this tomorrow, but you can see it's analytic using something called old-fashioned perturbation theory. So if you haven't heard, there's a beautiful technique called old-fashioned perturbation theory where you start with a usual Feynman diagram, and then you write it with the vertices ordered every possible ways. And then there's a set of rules that tell you that each vertex represents an expression where the k0 and p0 integrals are already done for you. So it's a trick to get one integral done for free. So you see now there's only vector integrals to do. It turns out that you can use this to prove that as long as your energy is low enough, you can never hit these poles. And therefore, if your energy is below 3m, this is a real analytic quantity. There's no need for an I epsilon prescription. It's nice and real and analytic. And then this is the final slide I want to show. So I've argued that M can be written in terms of this beta-Salpeter kernel together with all of these loops. I've argued that the beta-Salpeter kernel in the low energy region is just real and analytic, and there's no need for an I epsilon prescription. So the only place I need to think about I epsilon is for these 2 pions in the middle of the loops. And those are the only source of M being complex, and they're the only source of non-analyticities. So now we just need to study those loops in detail. We can come up with a cutting rule where I say, well, whenever I have a loop with 2 pions in it with an I epsilon prescription, let me just break that into its real and imaginary parts. And the real part is what we call a principal value pole prescription. That's also real and analytic. So it's only the imaginary part that's going to contribute something special. And you can prove when you take the imaginary part, you exactly get the function rho that was in the optical theorem. Rho just being proportional to the square root of s minus 2m squared. And so the final step is now everywhere you see a loop labeled with an I epsilon, you can replace that with the real part, the principal value, plus the imaginary part, the rho cut. And then you can regroup everything according to the number of times that rho appears. So if rho never appears, then you have just a whole bunch of loops with PV integrals. That defines the K matrix. And if rho appears once, then you have exactly that K. Then you hit the rho cut, and then you have K again. And that pattern continues. So you end up with the short distance K matrix by itself. Then the short distance K matrix hitting that long distance rho cut, where you're hitting that pole. And this is just a geometric series of the form 1 plus x squared plus x cubed. So it just has the form of 1 over 1 minus x. And you see we get a result which is exactly the result we had from the optical theorem. So whether you think optically or whether you think diagrammatically, you conclude that the scattering amplitude must split into 1 over the short distance K matrix plus this long distance branch cut singularity. And so here's just a slide summarizing that. So each channel generates a square root cut, and that means that if I'm thinking of just a single 2-particle channel, I really have 2 sheets. I have a physical sheet where I have, for example, bound state poles, and then I have a second sheet where the resonant poles can appear. And so it's really only by understanding those 2 sheets properly that we can understand scattering properly and understand resonances properly. And so those are the important lessons. These details matter for understanding quantitatively, and it's possible to separate the short distance and the long distance using the diagrams. Okay, so I will stop now. Where I had hoped to get, which would have been just a few more slides, but definitely too many for now, is by doing a very similar argument in the finite volume world, you get Lucher's finite volume formula. So we're very close to a finite volume formula that relates the energies in the box to physical scattering. That's something I will do at the beginning tomorrow, and then we'll go from there into more complicated scattering observables. But that's it for today. So thanks very much. Yes, I will at least give a couple. So the question is, how would you do this method for baryons? And yeah, the answer is that it actually works in a very similar way. So you essentially just need to add some extra labels to the kernel that represent the spin of the baryons. But it is understood and it has been done. Yeah, maybe I'll mention it tomorrow. But it works. So you can do this kind of proof for a baryonic amplitude in a similar way, and you can derive all of the finite volume formulas also in a similar way.